Broadcast is now starting. All attendees are in listen-only mode.
Good morning or good afternoon to everyone, depending on where you are. I hope you're all safe and well and working isolated from everybody else. It's a brand new experience for all of us. I know for myself, a lot of people would think I would just keep staying away from people, but welcome to the next installment of I-Gard's learning system, and this one is about smart versus standard high resistance grounded systems. But first, we're going to discuss why grounding is so important. When you have a ground fault, typically you have several types of systems: ungrounded systems, solidly grounded systems, resistively grounded systems. Here's one leading insurance company reported over 200 losses over a 7-year period related to ground faults. So ground faults happen all the time in industrial and commercial systems. So 72 of these were in commercial locations such as hotels, university shopping centers, convention centers, and 156 losses from manufacturing locations. The total losses that this one insurance company had to pay out was $180 million. So $120 million came from industrial facilities. On average, $769,000 in losses average per 156 claims. For commercial losses, $60 million, average $833,000. And you can see that a lot of the claims, particularly industrial, are well over $500,000 to over $2 million. So it's very, very costly to have losses over what is commonly referred to as the most typical kind of fault that you can have in an industrial facility or a commercial facility. And you can prevent all that with some minor changes to your grounding system. So the different types of grounding systems we have in our facilities are solidly grounded, which is about make up 52% of our facilities. High resistance grounding, 22%, low resistance grounding, 14%, and ungrounded systems still account for about 12% of our facilities. And the difference is basically how we ground our source. So ungrounded systems, usually a delta transformer, delta, ungrounded systems. There's reasons why people go with ungrounded systems, although the benefits are not really that apparent. A resistance grounded system far outweighs the ungrounded system. And a solid grounded system, because most people think it's economical to put in a solidly grounded system, so they choose that. And what we find is there are some people that put in a solidly grounded system who work from a specification and then turn over the property to an end user who is going to maintain that property. If the two parties worked hand in hand, and the people who built the property and the people who maintain the property work together, I'm sure they would come up with a better grounding system. But one is looking at, I'm sure you've heard about this before, green dollars and blue dollars. One is capital, one is maintenance. And if the two actually met, they would compromise and come up with a better solution, which is, I feel, most likely the high resistance grounded system. So we came up with an electrical safety risk meter. And so we've assigned numbers of 1 to 6 for different types of systems. For example, in column A, or box A, unscheduled process interruptions on first ground fault, typically $7,000 to $30,000 per hour for an outage. Now, $7,000 to $30,000 is not a lot of money. So there's a risk meter associated with that. the ability to locate the fault or the first fault in a timely manner. We'll assign a number from 1 to 6 in there, and we're going to use this to measure different types of grounding systems with this. Loss of critical process due to power outage, usually on a second ground fault. Now you're going to have a second ground fault on typically ungrounded systems and high resistance grounded systems. You're never going to have a second ground fault on a solidly grounded system, because whatever happens on the second ground fault on an ungrounded or high resistance grounded system would occur on the first ground fault on a solidly grounded system. Capital equipment, NFPA average $45,000 for equipment. Arc flash hazard, frequency and probability is going to be measured at this column of this row over here. And arc flash magnitude, there's a difference between the frequency of an arc flash and the magnitude of an arc flash. And those of you that were in the presentation 2 weeks ago will know that there is a complete difference. And if you haven't seen it, we'll probably post a link on it so you can go back and refresh yourself with how that works. Again, we're going to assign a number to each one of these boxes. We're going to add it up and find the electrical risk or electrical safety risk of the different type of grounding systems. So we're going to start with an ungrounded system. 12% of the facilities are ungrounded. Some people believe that ungrounded are really good. Most of the time, they're not really good. So with an ungrounded system, we have no intentional ground connection between the system, conductors, and ground. So no portion of A, B, or C phase, or L1, L2, and L3 are connected to ground. So it's a completely and totally floating system except for the capacitive loading or the capacitive coupling to ground. Ungrounded distribution systems are in industrial installations where people believe that they definitely cannot tolerate any interruption at any kind. They're susceptible to buildup of high voltages, up to 6 to 8 times on an intermittent sputtering arc flash. And I'll show you a slide on how that's done. The code requires that ungrounded systems be equipped with suitable ground detectors. There is no ground fault protection with an ungrounded system. There's only ground fault detection. Ground fault detection is measured each phase potential to ground. If you have, for example, a 480 volt system on an ungrounded system, you're going to measure 277 volts from all phases to ground on a healthy system. When one of the conductors touches ground, the potential between that conductor and ground is 0, and the potential between the unfaulted conductors to ground becomes 480 volts. So normally a ground detector would consist of 3 incandescent lights. And when the system is healthy, all 3 lights are on with the same brightness. When you have a ground fault, the faulted phase and ground, that light extinguishes because there's no potential difference. The faulted phase and ground are at the same potential, and that potential is 0. The potential is, we don't energize the ground conductor when we have a ground fault. What we do is shift the vector relationship with respect to ground such that the unfaulted phases are 480 volts, so you get 2 bright lights and 1 light that's out. So the 1 light that's out indicates that you have a ground fault. Unfortunately, it's a poor method of detecting ground faults because there's no difference between a burnt out light bulb and a ground fault. So just to fill in those numbers again, unscheduled process interruptions, it's very low, so we're going to assign a 1 to that. Unable to locate the first fault, you cannot find the fault in an ungrounded system unless you start cycling breakers open and close. Remember I said those 3 lights are the same brilliance when you have a healthy system. So if you cycle the breaker open and the fault is downstream from that breaker, you're going to go from 2 bright lights to 1 dim off light, or 1 light that's off, to 3 equally brilliant lights. And you'll determine that the fault is downstream from that location. So this is where I get a little bit of annoyed, because people choose ungrounded system because they can't tolerate any kind of power interruption. However, to find the fault, you need a power interruption. Loss of critical process due to power interruption on the second fault is high, because chances are, because it's so difficult to find where the fault is on the first fault, people don't look for it. So the probability of having a second fault that occurs on another phase is quite high. Capital equipment is high. Arc flash frequency and hazard is low, medium, and arc flash magnitude is high if you have, because it's based on the 3-phase bolted fault current. So 1,65536 risk meter is equal to 26, and that's quite high. So the Buff book says that ungrounded low voltage system employ ground detectors to indicate the presence of a ground fault. And again, we described that the ground detectors are bulbs, or if you have a high potential ungrounded system at 5 kV, you have to have grounding PTs, and then you load the secondary low PTs. So basically what you're doing is you're measuring the voltage with respect to ground. So the voltages, if you have a ground fault, one of the bulbs is going to go out. These detectors show the existence of a ground fault, but do not locate the ground fault. Very, very difficult to locate the presence of a ground fault in an ungrounded system. If the first fault is intermittent or allowed to continue, 6 to 8 times the overvoltages might occur on your system due to sputtering arcing faults. And this is because 6 to 8 times, because if you look at switchgear, I would imagine, the high pot level that we put on switchgear is about 2.2 kV. Anything above 2.2 kV with respect to ground, something is going to fail. So you're going to find that 480 or 600 volts, 6 to 8 times the voltage, you're going to be above 2.2 kV. So something is going to fail someplace. And it's probably going to be in a location not associated with the ground fault. We've troubleshooted many situations like this, and what people tend to forget is ground is this magic conductor, just connects your entire electrical system together. The Red Book states that overvoltage incidents associated with ungrounded operation reduce the useful life of insulation. So it is possible for you to damage your cable due to these sputtering arcing faults, where you can have puncture holes going through your insulation on your cabling system, because the weakest link in your system is going to fail. So you can see here how a system becomes 6 to 8 times the potential with respect to ground. Because neither the neutral nor the phases is connected to ground, when you get a ground fault, and we're going to assume here that the ground fault is on A phase, when you get a ground fault, A phase and ground are at the same potential. 1/2 cycle later, you're at 2 per unit above ground with A phase. Typically what's going to happen is the next restrike of the ground fault is going to be at the next peak sinusoidal part of the curve. So you're going to have a sparking arc when the sinusoid is at its maximum peak, and that's 1/2 cycle later. You could say this is the positive peak, this is the negative peak. So it's going to arc over, and you're going to shift that entire relationship down 2 per unit. 1/2 cycle later, you're up to 3 per unit. And the next positive restrike on the sinusoidal wave is going to shift this entire vector relationship up, and you can quickly get to 6 to 8 times the overvoltages with respect to ground. I don't know if you guys remember in school the RC coupling, tau. When you decay a capacitor is decayed at e to the minus t over RC. So the RC coupling. There is a C in an ungrounded system, but there is no R. So because there is no R, the time decay is very, very low. So it takes a long time for that arcing current or the potential to decay back to 0 volts. Here's an example of an automotive facility that had 485 events of peak voltages above 700 volts due to intermittent ground faults, and peak voltages of 1050 volts. Transient leads had insulation degradation due to these escalating overvoltages. And we'll touch more upon this later. Here is more damage that's associated with intermittent arcing faults. And you can see that there's very destructive overvoltages that occur and just totally destroy your system. Damage in this particular facility, I believe it was 15 kV, is in excess of $200,000. This wasn't due to a ground fault. This was due to an intermittent ground fault, which went undetected on an ungrounded system. And unfortunately, the overvoltages collapsed the entire system. FM Global says that ungrounded systems that phase to ground fault often produce dangerous overvoltages. Sustaining arcing faults in a low voltage apparatus are often initiated by a single phase to ground fault, which result in extensive damage. Again, reinforcing the fact that ungrounded systems are not good. And just goes on, unlike the ungrounded system, high resistance grounded system prevents transient overvoltages. You do get overvoltages when in a high resistance grounded system, but they're limited to 173%. So the next one we're going to discuss is solidly grounded systems. In solidly grounded systems, 52% of the installations, industrial or commercial, are going to be solidly grounded. And it may be for the wrong reasons, but they are solidly grounded. Employer facilities, owners, and managers who have responsibility for facilities and installations having electrical energy, and you guys all know this, is 70E and Z462. Electrical hazard risk assessments are performed during the design of electrical system installations. One thing we have to do is reduce the likelihood of exposure and reduce the magnitude or severity of exposure. Solidly grounded systems have a high probability of having a single phase to ground fault propagate to a phase-to-phase or three-phase fault. And basically what happens is there's so much energy being produced in the single phase to ground fault that we have molten steel, molten copper, and a lot of debris contaminating the insulation. Air is insulation, and if it becomes contaminated, it becomes a better conductor, thereby creating a phase-to-phase or three-phase fault. The solidly grounded system has the highest probability of escalating into a phase-to-phase or three-phase fault, particularly in 480 and 600 volt systems, because your voltage gaps are reduced at 480 and 600 volts. Here's an example of a solidly grounded system where they had an intermittent arcing fault. This was on a 600 volt system at a commercial facility. The owners believed that they were trying to economize the installation by putting in fuse switches, and because of a ground fault that occurred, the entire facility was down for several weeks, and then they had to put in backup generation to keep the facility going again. But again, one person believed, or the owner believed, that they were saving money by putting in a grounded system in a facility that required high reliability, such as a hotel. In this particular example, unscheduled process interruption is very high. Both the NEC and the CEC dictate that if you have a system that's greater than 150 volts to ground, greater than 1,000 amps, you must have ground fault protection. So to meet the minimum code requirement, we put ground fault protection on the main breaker. That example we saw here had a 600 volt switch with ground fault protection and fuses everywhere else after that. So the only place you could put ground fault protection was on the main isolation device. Unable to locate the first ground fault in a timely manner. Well, we didn't find the ground fault, sorry, the owners didn't find the first ground fault in this location until the entire system caught on fire. Loss of critical process due to power interruption. That's very low because you're never going to have a second ground fault. This was caused by one ground fault. Capital equipment is high. Arc flash energy is quite high. You can imagine the destructive nature that caused this kind of damage. And arc flash hazard was very high. So a solidly grounded system was 26 on the safety risk meter. One of the professors at Johns Hopkins University did a lot of testing on solidly grounded systems and arc flash protection, arc flash incident energy. What they found is any arc that was low in nature and the duration was very, very low, if it fell below this green line, then you had superficial smoke damage. Any faults with arcing fault current and duration that were between the green line and the red line had surface damage, and any faults above the red line in fault current and duration burned through the steel. So you can see it doesn't take much. For only 600 milliseconds and 3,500 K, 3.5 Ka of arcing current is enough to burn through the steel of an enclosure. So you can imagine in a solidly grounded system how much destructive current there is. You could put in an arc flash sensor, and if you put in an arc flash sensor, you're going to detect the presence of the flash quickly in a solidly grounded system, and you're going to isolate much more quickly. But all we're basically going to do is lower the magnitude of destructive current. We're not going to lower the probability or the frequency of the flash hazard, and everything else stays the same. So we went from 26 to 21 in the risk assessment meter, but we've made it safer by implementing arc flash relays. So we lowered the magnitude or severity of an arc flash, but we haven't lowered the frequency of an arc flash. And many of you who were at the presentation from 2 weeks ago was discussing why high resistance grounding is an arc flash mitigation technique. Again, we can circulate that link again, and you're free to look at it and determine why NFPA 70E and Z462 have established high resistance grounding as an arc flash mitigation technique, because it lowers the frequency, not the magnitude. So high resistance grounding system, 22% of the facilities are high resistance grounding. And the easiest thing to do is to put a resistor on a 480 volt system. You could put a 55 ohm resistor here and lower the fault current to 5 amps when you have a single phase to ground fault. Oh, that missed. Sorry about that. High resistance grounding, if you limit the fault current on 4160 volts, 5 kV systems, to 10 amps or less is an arc flash mitigation technique. By limiting the ground fault current, the fault can be tolerated, and you can shut down in a timely manner, or you can keep the system working and find where the fault is with pulsing techniques. Dumpty Jacobs wrote this book, excellent book. 95% of all electrical faults are phase to ground faults, and they propagate to phase or three-phase faults if they're not limited to 10 amps or less on systems 5 kV and below. High resistance grounding helps ensure that ground faults of a known magnitude, helpful for relaying purposes. This makes the possibility of identifying the faulted feeder with sensitive ground fault relays. High resistance grounding provides the same advantages as ungrounded, meaning that you don't have to isolate, except you don't have the disadvantage of escalating overvoltages. And ungrounded systems offer no advantages over high resistance grounded systems in terms of service continuity. So that facility that we saw earlier, we converted that system from an ungrounded system to a resistance grounded system, and we went from 485 peak voltages over 700 volts, and the peak voltage at 1050 volts to 0 peak voltages events over 700 volts, and obviously, and the peak voltage was 660 volts. So it improved this facility tremendously, specifically because of the peak voltages were reduced, and we didn't have any of those transient over voltages we had in the ungrounded system when we converted to the resistance grounded system. Again, high resistance grounding. A great majority of electrical faults begin as the phase to ground type. When high resistance grounding is employed, you insert an impedance, and if you limit that fault current to 10 amps or less for systems 5 kV and below, it leaves insufficient energy for the fault to propagate to a phase-to-phase or three-phase fault, and thereby becomes an arc flash mitigation technique. So standard HRG, the minimum requirements, you need a resistor to limit the fault current. And believe me, we've seen a lot of systems. I've seen people use stove elements as resistors to create a high resistance grounded systems. You need an ammeter to measure the voltage, the current, and you may or may not use a voltmeter to measure the voltage. You should have a pulsing contactor to help you locate where the fault is. Now, this alone will allow you to have your system maintained constantly so that you don't have to shut down when you have a ground fault. It helps you locate where the fault is, and you have an arc flash mitigation technique with standard HRG. That's a given. We can have this. Now, a lot of manufacturers are going to say they're going to have communications, data logging. So let me give you an example of what standard HRG is going to give you in terms of data logging and communications. You have a fault. You don't have a fault. You have a fault. You don't have a fault. The fault is here. The fault is not here. That's what you're going to get in communication, because the only thing you're looking at is you're looking at the current going through the resistor, or the voltage from the neutral point to ground, or the current going through the resistor. That fault can be anywhere in your facility, and data logging or communications on standard HRG is like saying when you have a headache. You have a headache, you don't have a headache. You don't know how to get rid of it, but it's there. So for a data center with standard HRG, typical data centers have a transformer and a generator. There's usually no tiebreaker in between these two because you're either on the transformer, and if you lose your power, you're on the generator, but you're picking up the same load. So basically, these two breakers are interlocked so that only one of them is on at one time. When you have a data center with high resistance grounding, what's going to happen is you're going to have a ground fault. And if you're on utility, this HRG system is going to tell you when you have the fault. And when you're on generation, this HRG system is going to tell you when you have the fault, because we're looking at the current going through the resistor here, or the current going through this resistor here when you're on generation. The fault is down here. This is where the fault is. The return path is either going to be the transformer if this breaker is closed, or it's going to be, let me change the color here. Or it's going to be the generator if this breaker is closed. So the operator, the maintenance people looking at this system are going to have to look at two different locations to determine if they have the ground fault, depending on whether the transformer is supplying power or if the generator is supplying power. And sometimes the generator is going to be in a far further location because you don't want to have all that noise inside your data center. So you have to look at a different panel to determine if you have a ground fault in a data center. So because you have high resistance grounding with a standard HRG system, your unscheduled process shutdown is going to be low. Your ability to locate the first fault is going to be low because you have pulsing and you can find where the fault is. Loss of critical process due to the second fault. If you have a second fault that occurs on a different phase, and let's assume we have a different meter, something is going to shut down. You don't know what's going to shut down. It could be this breaker, it could be this breaker, or it could be the main, depending on how the relay coordination is set up. Capital expenditure is medium. Arc flash hazard frequency is lower because we employ a resistance grounding system. So we could say that NFPA 70E and Z462 have established that high resistance grounding is an arc flash mitigation technique simply because the probability of having a phase-to-phase or three-phase fault is quite low. And the arc flash hazard magnitude is medium. So we end up with 16. Smart high resistance grounding. Minimum requirements. You need a resistor to limit the fault current. That's a given. You need a pulsing contactor because you want to locate where the presence of the fault is. Can't have an option for resistor monitoring because unlike the US, Canada has the need in the code of finding where if there's a fault in your resistor. Feeder indication. You should have the ability to determine where the fault is in your system at a glance. For example, the fault is in feeder number 5 in this system right here. So right away, you start looking for your fault at the location where it's safe to look at, rather than the standard HRG system that says you have a fault, the fault is gone, you have a fault, the fault is gone. Now you can have a system that says you have a fault that's on feeder number 5. Initiate the pulsing and then start looking from that for that fault from feeder number 5 down because you've already got a starting point of where to find it. So it's easier to find the fault. More importantly, it's safer to find the fault because you right away, you're driving people away from your main switchgear where you have the highest level of incident energy. You're looking downstream from the fault for where that fault is because you've already given a starting place. We've eliminated all the other feeders. We're only looking at feeder 5 because that's where it's telling us we have the fault. So we start looking downstream when you turn on the pulsing. You have SIFT, or you have an adjustable timer. SIFT is Selective Instantaneous Feeder Trip. It's a mouthful. But what it means is when you have a second fault that occurs on your system on a different phase, on a different feeder, you have a phase to ground to phase fault. When we had the system here before, we weren't able to tell which breaker was going to trip. It could have been this one, it could have been this one, or it could have been the main. With SIFT, you're able to detect or determine which breaker is going to open because you, as the maintenance person, are going to put in a priority number from 1 to 16, or from 0 to 15 actually, as to how important that feeder is to you. So the more important that feeder is to you, the higher priority number you have, and the higher priority means that the most critical process in your facility is going to shut down last, and a lower priority number is going to shut down first. In Canada, we use a lot of high resistance grounding, and we use a lot of smart high resistance grounding in hospitals because the operating room can never shut down. It has to stay up, and it doesn't matter if everything else is collapsing around it, the operating room has to stay up. So it usually has the highest priority level. And we can have an arc flash monitor. At I-Gard, we listen to what our customers say. And our customers sometimes say that ideally, I like the high resistance ground system, and I like the idea that you can have a lower probability of having an arc flash. However, I want to have my cake and eat it too. So not only do I want to have a lower probability of having an arc flash, I also want to have a lower incident energy level. So we developed an arc flash module that you can connect to your smart HRG system and interlock light, or have light only, or light and pressure to trip the main breaker should you have an arc flash, giving you the ability to both lower the probability of having an arc flash as well as lowering the magnitude of the arc flash. So our risk meter now looks like this. Unscheduled process interruptions, 1. Unable to locate the first ground fault in a timely manner, that's not an option. We can locate it very quickly, and we could typically locate a ground fault with this system in less than an hour in any size facility. I've had this challenge with the place where I live, where if we put a ground fault on your system, if I don't find it in less than an hour, I pay for lunch for everybody in the facility. I have never had to pay for lunch because we've always found the ground fault in a timely manner, less than an hour. Loss of critical process due to power interruption, 1. Capital expenditure, 1. Capital damage, actually, there's no damage. In fact, once you employ a resistance grounded system, you have less damage at the point of the fault because you have non-destructive current. Arc flash hazard frequency is very low, probability of that, due to NFPA 70E and Z462. And the arc flash magnitude now is low because we trip when we have an arc flash, so we're able to lower the incident energy because incident energy is directly proportional to time. The faster we clear that fault, the lower the incident energy. So with the smart HRG system, your risk meter goes down to 6. Well, let's look at an example. A data center now with smart HRG. Instead of having 2 HRG systems, high resistance grounded systems, one at the transformer and one at the generator, we now have 2 resistors. 1 resistor at the transformer, 1 resistor at the generator, because we're looking for ground faults. More often than not, ground faults occur in the loads, not in the sources. So we could have our ground fault sensing equipment with a feeder on each, or a feeder module on each separate feeder, telling us where we have the fault. The ground fault doesn't care whether we're being fed by the generator, in which case it would take this source back, or whether we're fed by the transformer. And take this route back to the source. Ground faults always have to return back to the source. So we have one HRG system, so the operator of that facility looks at one location and one location only to determine whether they have a fault, ground fault on their system or not, because it's independent whether they're running on the generator or whether they're running on the transformer. The fault doesn't care where it's coming from, it just cares where it's going to, but it's coming from the origin of the fault, which is right here. And now when you turn on the pulsing, it's telling you, you look in feeder number 1, 2, 3, 4, 5, 6, 8. Feeder number 8 has the ground fault. Start looking here. You've eliminated 7 feeders where your incident energy is going to be the highest. And the maintenance personnel could start looking from here, and this can go to an MCC. Once you turn on the pulsing, it doesn't matter where that fault is, you're going to locate where that pulsing is everywhere. Well, only in the faulted path. Not everywhere, sorry. You're only going to find the fault where in the faulted path. So if you see the signature, you're in the faulted path, keep going downstream. You're only looking at one location to determine where the fault is. You have a central location, but the feeder modules can act independently as well. So if you get a second fault here, and let's assume this was a, let's assume this was a data center. So this was protecting your main chiller. And if the chiller goes down, the entire system is going to have to be shut down. And this is feeding the cafeteria. So if you have a choice between the cafeteria going down or the main chiller going down, you're going to choose that the cafeteria is going to go down. So you're going to assign this feeder a lower priority than this feeder. So this will be a priority 1, and this will be a priority 15. So it basically means if this fault occurs and any other fault in the system occurs, this one is guaranteed to stay closed and energized for a lot longer. So reducing the likelihood of exposure, high resistance grounding. To reduce the magnitude or severity of the exposure, use an arc flash relay or an active arc mitigation system. With the SMART HRG system, you can do both. You can have the benefits of the high resistance grounding system and follow this here, and you can reduce the magnitude by using an arc flash relay here. Again, these are some of our products that we have for ungrounded systems. We're a ground fault company that can provide solutions for any type of grounding system you have. We specialize in resistance grounding, but we also have ground fault protection systems or ground fault detection for ungrounded systems. And remember I said earlier that we had the 3 incandescent lights. We come up with a indication here called the VIA, voltage indication alarm. It's a ground fault detector for ungrounded systems. So rather than having a negative reaction or a negative indication that you have a ground fault in an ungrounded system by having one light go out, what we have here is 3 LEDs, and when all 3 are green, that means you have a healthy system. When one phase is faulted, the faulted phase is going to turn red, giving you a positive indication that you have a ground fault, not a negative indication that you have a ground fault. And for solidly grounded system, we have ground fault protection relays that can go up to 1200 amps, arc flash mitigation systems, pressure switches, and ground fault monitors. So why partner with I-Gard? Well, first of all, we listen to what you have to say. If you have a problem and you want us to solve something, we will design a product that will help you meet your needs. So we're a solution-based company, not necessarily a product-driven company. We use our products for different features, but we actually listen to what our customers say. And because we're a high resistance company that produces the relays and the resistors, we can basically come up with anything you want. Any other high resistance grounding companies are really going to provide you with their resistor and a off-the-shelf relay someplace, where ours are married together because we produce both. So to summarize, an ungrounded system, you get process continuity under ground fault conditions. You're not going to get that in a solidly grounded system. You're going to get control of transient overvoltages, yes, because when you have a ground fault, you're never going to have transient overvoltages. The ability to locate the ground fault, well, you want to trip the main breaker, and then you look for where the smoke is. High resistance grounded systems, you're going to get the process continuity, and this is a standard HRG systems, and we make those as well. You're going to control transient overvoltages, because the transient overvoltages is basically going to be at 173% of the voltage, line to neutral voltage. Ability to locate the ground fault. Yes, we can do that because the ground fault is going to have pulsing, and we can locate where the fault is. The Sentinel with HRG with arc flash module is going to give you everything. It's going to give you the process continuity with the second ground fault and arc flash mitigation, because we have the arc flash relay in here. So we're going to have that. With the Smart HRG, without that module, you're not going to have the arc flash mitigation for safety. So we went from 6 on this one, and this one I believe was a 10 on the safety meter. And with that, I'm going to turn it over to you guys. Are there any questions?
Thanks, Sergio. That's great. Yes, we actually did get quite a few questions. We have a few about wanting you to explain the pulsing contactor a little bit more, how it works locating the fault, and then also if you have a ground fault detection relay on every feeder, do you still need a pulsing contactor at the resistor?
Yes. Okay, good question. And you know what, to answer that, I'm going to work on one of my presentations from a previous presentation, which you're able to see. And again, we have the ability, Jessica, we can send out the link to this one as well, right?
Yeah, of course. It's probably already online under our presentation tab, but I will double check. And if it's not, we can upload it online for everyone to reference.
All right, so this pulsing contactor right here. This pulsing contactor changes the value of the resistor. So remember, we limit the fault current to 5 amps. So we can change that fault current by changing the value of the resistor. On a 480 volt system, 5 amp pulsing, you're going to have a 55 ohm resistor. So let's assume we're going to change the value of that resistor from 55 ohms to 27 ohms. When we do that, we change the fault current from 5 amps to 10 amps. And we do that cyclically. For example, 1 second that contactor is closed, another second that contactor is open. So when we turn on the pulsing, what we're doing is we're opening and closing that contactor. When we close it, we have 27 ohms. When we open it, we have 55 ohms. That means the fault signature changes. So if we have a ground fault here, the only place for that fault current to go back is through this resistor. So now our fault current, you can see that the pulsing only exists in the faulted path. The unfaulted feeders, you're looking at three-phase current, zero sequence current, which is going to be zero. It's always going to be zero. Once you pass the point of the fault, it's going to be zero. Only in the fault, once you pass the fault here, you're measuring zero. So you can measure, you can find the actual pinpoint of where that fault is by using this method. Now, the second part of that question was, do you still need feeder indication? I think you do, because the problem is this is an ideal situation. Unfortunately, in a non-ideal situation, you're going to have capacitances on every system to ground, so you're going to have a little bit of current on every feeder, measuring that capacitive coupling. But only in the faulted path will you see this pulsing, because this capacitance coupling here is going to be voltage dependent, and the signature of the current going through here, through the fault, is going to be impedance dependent. So you need to change the value of the resistor to actually pinpoint where your fault is. Long answer, but I hope you understand it.
Perfect, thank you. Next question, what are the advantages and or disadvantages of B-phase grounded systems? How difficult is it to switch from B-phase to HRG?
There's one company that uses a lot of B-phase grounded systems, and sometimes it's easy to change, because if you have a true three-phase network, you're probably not going to have any fuses on B-phase. So you have to put in a fuse on B-phase. It's very, very easy to change a B-phase grounded system, if it's the traditional B-phase grounded system where you have all three phases there, to a high resistance grounded system by employing a zigzag transformer and a resistor. Everything else stays exactly the same. But I've been to some places that have B-phase that only have two fuses, one for A and one for C, and nothing there other than ground for B. So for those systems, it is very difficult to change over.
Okay. Next question, is there a rule that says 600 volt or 5 kV systems have to be HRG?
No, but I wish there were. It's much safer to have a high resistance grounded system than a solidly grounded system. And if you look at the damage, which we had here, it is more economical to have a high resistance grounded system, because again, over a 7-year period, $180 million was paid out by an insurance company simply because of ground faults. So it's going to be more economical, but what we need to do is have the people who are building facilities talk to the people that are maintaining facilities, so that the cost of the and it's not more costlier, I don't know if that's a word or not, but doesn't cost more to put in and employ a resistance grounded system rather than a solidly grounded system, and you end up having a much safer system. And I believe, Jessica, we have the economic guide on the difference between resistance grounded system and solidly grounded system. Can we post that on our website too?
Yeah, that's online, but we'll be sure to distribute that to everyone when we pass out this recording, just so it's easy to access. And with that being said, I think we're approaching the 3 o'clock mark, so we don't have more time for questions. We do have quite a few that we didn't get a chance to answer, unfortunately, but we do have our Q&A coming out next Tuesdays, so that will address everyone's questions, and we will pair a few great articles, such as the economics of HRG, with that. As for the recording and the PDF of Sergio's PowerPoint slides, that will all be available online by tomorrow. So you can rewatch the recording, download the slides on demand whenever is convenient. And then also, if you have any more questions to submit, feel free to email jcraig@i-gard.com, and we will continue taking questions to include in our Q&A booklet. Sergio, anything else from you?
Yeah, I just noticed one of the comments was about a low resistance grounding system. We didn't discuss that here because well, we just simply ran out of time. We could have if you're interested in it, we can have another topic about the low resistance grounding system.
Yeah, absolutely. Okay, I think that concludes today's webinar. Thanks for attending, everyone. Stay safe. And like I said, feel free to email us with any questions you want to add or keep submitting them until the 3 o'clock mark. Okay, thank you.
Thank you. Everyone stay safe.